Good. So the last day, we dealt with fundamental quantities, right? For some reason, I'm not seeing my... And we looked at some what we call the basic or the base quantities in physics, right? We also talked about what we call derived quantities, right? So another way of looking at quantities is what we call scalar quantities and vector quantities. Somehow I should be seeing my...
So try clicking on the cursor at the bottom of your left hand. Another one.
Oh yeah,
Yeah.
yeah. I think I'm okay now. Yeah, yeah. I think my hands are oily. That's why. Yeah. So another way of looking at quantities in physics is by looking at them as what we call scalar quantities and vector quantities. Now, what are scalar quantities? What are vector quantities?
So, um, vector quantities are quantities that has magnitude and direction, while scalar only has magnitude, but
Very
no.
good. Yes, yes. Right? So scalar quantities are quantities with magnitude, or size. You know, like, okay, let's take some examples. Mass, right? Time. These quantities are two examples, right? And out of the base quantities, these two, you think of them as, okay, they have a size, like you talk about 2 kilograms. Nothing about direction. You don't have 2 kilogram north, right? You talk about time, 10 seconds. You don't... time don't have direction. I know there's this argument that time moves forward all the time. But when we speak of direction, we're talking about whether we can point in the direction on the earth then, right? In the physical space. How we're doing physics, right? So while we might say, okay, time moves forward, that's not a direction in space, right? It's not a direction in space. That's a more abstract idea that, well, time just goes forward, but it's not something we can point to in space, right? As compared to, and maybe when I illustrate it with vector quantities, vector quantities have magnitude and direction. Have magnitude and direction, right? And for example, and maybe to show you the difference, let's take the quantities distance as against displacement, right? Now, these two, they're different in that distance is what we'll call a scalar quantity, while displacement is what we'll call a vector quantity. Now, let me illustrate it. Let's say you are down here, you're standing up down here, and you're walking on a path going this way. Maybe this is, all right, 10 meters. And then you walk here, and this is 20 meters. And you end up here, right? The distance that you have traveled, right? Distance traveled is equals to 20 meters. Sorry, 30. 10 meters and the 20. It's as though you added the two lengths, right? So your distance traveled is 30 meters. However, your displacement from your original position is this length here, right? And well, you'd have to use something called Pythagoras theorem to find this. I don't know You remember that from high school. So this distance is going to be 10 square plus 20 square root of that in meters, right? Can somebody help me with that? That's how much? Square root of 300, let's see, what, 400 or 500?
Sir, the answer is 22.36.
22, all right, 0.36 meters, right? So your displacement is like the shortest distance, right? From where you were and where you end up. And you can actually say that it makes, all right, you can say it makes an angle. Let me say we find this angle here. Let's say that's alpha, right? And alpha, we can say that, all right, tan alpha is equals to 20 over 10, right? Opposite over adjacent, which is 2. So alpha equals tan inverse of 2, which is, can somebody do that for me? Tan inverse of 2, give me an angle.
63.43.
All right, 63, all right. We can probably round it to even, all right, let me go with the 43 degrees. So your displacement, if you were here originally and you end up here, your displacement is, and if you were to put some direction, and here is where you will see that when you talk about time moving forward, it's not really a direction, right? Let's say this is north, right? So you will say that your displacement is, what is it? 22.36 meters. Displacement is, let me see if I can move this up a little. Displacement equal 22.36 meters, making an angle of 63.43 degrees with the north axis, right? A little bit of mathematics, you can even write this as a bearing, right? Where you write 0, 22, or let me leave the decimals out. 0, 22 degrees, right? On a bearing, you can say the displacement is 22.36 meters on a bearing of 0, 22 degrees. Because when you talk about bearing, you're talking about measuring the angle from the north going clockwise, right? So you see how much more displacement involves, right? It involves direction, right? So a scalar quantity just has magnitude, end of story, right? And we had some examples there. And maybe you could jot down, right? Ask the internet for five scalar quantities. Ask the internet for 5 vector quantities. So don't just stick with these 2, right? But just remember the basics, that a scalar quantity has magnitude only. A vector quantity has magnitude and direction. Good. Now we got a little taste there just now of how we add vector and scalar quantities. Did you notice how you did it very linearly with a scalar quantity? When you were dealing with the distance, right? When you were dealing with the distance, what did you do? You simply add 10 and 20 very, very linearly, right? If you you buy 5 kilograms of potato, right? And you buy 2 kilograms of chicken, you know, the total weight of your bag is going to be the sum of these two, right? 7 kilograms of, household or groceries, or what you call it, right? You add them linearly. Very easy. But when it comes to vector quantities, they can get very technical. You don't add them linearly so easily, right? And we want to get into that a little bit, right? And again, to illustrate with time, right? Time, yes, you all say going forward, but when you add time, you just, okay, you take 10 minutes to travel home and you take 10 minutes to eat. Therefore, you're going to take 20 minutes before you come to the class, right? Before you log in, maybe you take another 5 minutes. You just add up all the time and say, man, you know what, I'll take about 25 to 30 minutes to join class because of traveling, eating, and taking the time to log in. You just add them linearly, right? But with vector quantities, adding them is very technical. You got a glimpse of it just now here, right? You got a glimpse of it. I'm going to go back to the example just now. And I'll show you how, all right, we started off here. And you walked up, okay, 10 meters. Now this 10 meters, you can think of it as a vector quantity as well. Right? You can think of it, because you can say you walk 10 meters north, and that scalar quantity that you were treating it changed now. You are now treating it like a vector. And then you can say you walked 20 meters east. Now, this 20 meters is no longer scalar. You're treating it now like a vector because you add on direction to it. So your displacement is the sum of these two, right? So if you were to, you know, and normally we represent vectors with arrow diagrams. You can put the arrow here. You can put the arrow at the end here too. We can put the arrow here. And then you call this, or you end up here now, your final position relative to where you were initially. That distance from here to here, we call it displacement. And we put two arrows, and we are saying that this displacement is the resultant of these two other vectors, right? So we're not treating 10 meters just like a distance. No, we add something to a direction, right? You say, okay, you walk 10 meters north, then you walk 20 meters east. What is your resultant displacement? Right? So your R now, your R is going to be equal to, and then is when you do your Pythagoras theorem thing. And then you'll find this angle here, right? And then you will say that, okay, alpha equals so, and then you'll state your conclusion that your displacement is so much at an angle of so much with the north axis, right? Now, adding vectors can get fairly complex, right? Not always will you have these nice right angles, right? Not always will you have these nice right angles, right? You can have a situation where vectors are at very odd angles to one another. I'll show you an example in just a moment. Open up the space for some breeze, boy. Yeah. So let's take a situation. You have an object, maybe on a surface. I don't know if anybody here is working in a warehouse, right? Anybody working on in a warehouse? And maybe you have to pull something. If you're pulling this object, you usually pull at an angle, that's all. You're pulling at an angle.
To increase force.
I didn't get that.
To increase force, sorry, correct.
Yeah, because of, I mean, you wouldn't be pulling like this, right? Because if the object might be, let's say it's a small object on the ground, fairly heavy, and maybe you have it, all right. Maybe you want to argue that I should have put it on maybe a trolley, right? All right, this thing is on a nice little trolley. I was asking if anybody works in a warehouse here. They have the thing on wheels, you know, right? Good. So this object is up here, and the trolley has a handle, and you're pulling here. You don't usually pull here, right? Because the trolley might be lower down on the ground, and you are maybe you're a big person, you know, like this here, right? You hold on to. I got it wrong. You need to be a bigger person. Let's say you're way up here, right? So you're way up here, and you know, and you hold on this thing, and you're pulling, right? You're pulling the thing. So your force makes some angle here. Your force makes some angle here, right? It's not horizontal. It's not horizontal. No, it's not horizontal. But what you realize is that there might be a force that is acting this way, right? A force that is acting that way. And I'm going to use F here because later on we're going to be introduced to a resistive force called friction. So there's some kind of friction going on between the trolley wheels and the ground, right? Especially, you know, your trolley has some, let's say, rubberized wheel. So it will give you some resistance, you know. Good. So you want to know, well, all right, how much force you need to pull with to overcome this frictional force to get this thing moving, right? So you'd want to get to know that. So how do you do that? But the force you have here is actually acting up that way. It's acting at an angle, right? Good. So what you need to do then is to, there's a word they use, you resolve this force downward, right? You resolve it horizontally. And when you resolve a force, this same force here, it's as though this force you can break it up into what we call its components. I could break this force up into a vertical component as well as a horizontal component, right? For this problem, I'm going to stick with the horizontal component. So the horizontal component, I'll put an arrow like that, meaning horizontal component, right, is equal to P cos theta. If you wanted to know the vertical component, I'll tell you it's going to be P sin theta, right? And there's a bit of trigonometry behind it. I'll show you in just a moment. Good. So I just want to show you how being able to resolve a force is important. So you resolve the force, and now you can calculate. You can say that, all right, if the frictional force is F, and you're exerting P here, you got to ensure that P cos theta must be slightly greater than F to get this thing moving, right? P cos theta must be greater than F, or else you can't pull this thing forward. Is that clear? You agree with me? The force you are exerting here must be greater than F for this thing to roll. And if I'm to add in, you know, what our main concern in this course, right, is that you're talking about occupational health and safety, right? And you don't want to load this thing up. Maybe your boss says, you fetching one thing whole morning, when we got done this work, and he actually tell you to pack on so many crates maybe on this thing that the force you can exert, right, times the cost of this angle is not greater. Because the more you add on here, you'll learn later on that F is equal to something called mu R, where mu is the coefficient of friction. Coefficient of friction, right? And it's a number usually between 0 and 1, right? Some fraction. And R is the way you call the reaction force. It's usually equal to the weight, right? So the weight of this whole setup here is going to act down, mg, right? And then the ground is going to react to that weight by R. So the frictional force is calculated from mu times R. And mu, well, that will depend on what the wheels of this trolley is made of. Is it made of rubber? You know, so I've seen trolley with steel wheels, right? Steel. But mostly you get rubberized wheels, right? So you have to ensure that the frictional force, in other words, if I'm going to go up here, P cos theta is greater than mu R, right? You have to make sure that this is so, or else you're going to strain yourself. You will have to, if this isn't true, you have to increase P, right? If the frictional force is so heavy that like you pack a whole set of boxes on top there, or beverage, like they have a beverage company at the head of my street here. But they don't use trolley like this so much. They have these, what do you call them? Why is the word eluding me now? Forklifts, right? And they pack the boxes on pallets, right? But I do see some guys sometimes just to move little bits of stuff into the building. They might not use a forklift. They have the same trolley and they pack on a couple of boxes and they'll roll it in, right? But you have to ensure that the force you are exerting is such that it's going to be enough to overcome the frictional force, right? And once you get the thing rolling, again, is there anybody who does, I mean, anything where they have to put stuff on a trolley and pull it and so? Nobody? Your work doesn't involve that? I know there are some nurses in here having a patient on a bed that is rolling. This is something similar. I can't, of course, get examples from every profession in the room, right? But again, the same thing applies, right? You might, let me go to the nurse. Maybe the nurse, they have a patient on the bed and they got wheels here. And they might be pushing the patient lying down there, and you have to push, right? So when you push, all right, you're using a pushing force. The frictional force is acting this way, right? And you have to make sure that P, let me go to F, is greater than F, right? For it to get moving. Anybody here, when you are pushing or pulling, let's say a trolley, do you notice what happens as you're trying to get it moving? And when it starts to move, do you notice any difference?
Yes, sir. It feels different in weight.
Okay, tell me a little more. The force you have to exert to get it moving, is that greater or less than the force that you have to exert to keep it moving? Which one?
So it's always harder to move, and then as motion takes place, it gets easier as it rolls, depending on direction, the load, etc., etc. But generally, it's the same.
Yeah, that is so true. Give me a second. I want to switch on this light here. 1 second. Yeah, that's a fact. That's a fact. The reason why, and I just want to give you a little reasoning here, right? That the frictional force, there's something called static friction. Static friction. And they have dynamic friction. Right? Static friction is that frictional force that opposes the motion before the object begins to move, right? So you have something, let's go back to, all right, we have an object here. I'm going to use a horizontal force, right? I'm going to use P, and friction is going this way, right? Good. So you will find that when you have an object and you start to exert a force, it seems as though this frictional force increase to the point where they call it limiting static force, limiting static frictional force. In other words, it goes to a maximum just before this body starts to move, right? But once it gets moving, the frictional force tends to get a little less. And that's what we call dynamic frictional force. So usually, static frictional force is greater than dynamic frictional force, usually, right? And you would notice that once you get a bed, let me say you're in the hospital, and you got to push a patient, once you get a bed rolling, you want to know what's going on, the bed rolling, and you're hardly exerting anything. The reason why is that the force you are exerting then is just to overcome the frictional force, right? But when you have to get it moving, two things are working against you. The static frictional force is greater. That's one. You have to overcome that. And secondly, you have to give it, and when we reach there, later on, we'll talk about something called acceleration, right? So you got to get his body accelerating, because remember, it's at rest. It's not moving. So you have to create acceleration, right? And notice, acceleration is related to force. And the force needed depends on not how much acceleration you want to produce, but on mass as well. F equal ma, we'll come to this a little later, right? So the force you have to exert depends on two things: what acceleration you want to create, and secondly, what mass you have to push, right? You see? So if I'm going to use P for this F, right? Before you confuse it with friction, P, right? So P, let me write that back. So P has to overcome two things. It has to create acceleration on a mass, plus it has to overcome static frictional force, right? And when it starts to move now, sometimes you don't want it to accelerate too much. You just want to get it going, and then you reach a certain speed and say, oh, that's okay. So this comes out of the picture. And all you have to overcome now is not this, but the dynamic frictional force, which we say is less than this. And that's why it's easy, right? Once you get the thing rolling, you're okay, right? You're okay. You just have to overcome the dynamic frictional force, because you're not accelerating. You achieved a certain speed and you want to stay there, right? I've gone overboard in that I deviated from what I wanted to talk about, which is the resolution of the force. Like, as I said, you're exerting a force at some angle, right? You're exerting some force. And maybe you want to take this force, and you don't want to do any calculation or any estimation with the force at this angle. You want to do it maybe horizontally or vertically, right? You want to take this force and kind of break it up into its components. So the component horizontally is going to be P cos theta, where this is the angle theta. And vertically is going to be P sine theta. And I did say I'm going to show you why I can say that this force can be broken up into these two, right? Let me show you. Let's say I want to take this and add them to get this. I'm going to use Pythagoras theorem, right? Because in vector addition, it's as though I can take this force and shift it along here. So I can take, okay, so this here is P cos theta, all right? Up here is P sine theta, right? And the resultant, which is P, I can put 2 arrows there, is the resultant of these two. And how do you add them? You use Pythagoras theorem because this is a right angle. So P sine theta square plus P cos theta square, the square root of all of that, is equals to P. And this here, when we simplify it, you get P square sine square theta plus P square cos square theta equal P, right? Well, I shouldn't say it's P. Let me show that it's going to be equal to P. It's going to be equal to P. We know it's going to be equal to P. Let me show you how that happens. So this here becomes P square bracket sine square theta plus cos square theta, right? Now, there's a bit in mathematics that says sine square theta plus cos square theta equal 1. So this whole piece becomes 1. So all of this becomes square root of P square, which is P, right? So what we are seeing is that when we add P cos theta and P sine theta, when they're at right angles to one another, we get P, right? When we add them, we get P. Therefore, we can take P and break it up into P sine theta and P cos theta back, right? Into its components. We can do that. You see? And usually in physics, we normally would, especially if you're dealing with a horizontal surface, things are moving on it. We might very well be resolving in the horizontal direction and the vertical direction. There are cases, so let me just show you this here. When something might be on a slope, and you might want to, all right, the weight is this way, all right, mg, the frictional force might be that way, and then this mass here, we can, the force that it exerts, the weight, mg, we can resolve it this way. So going down here is going to be, let's say this angle is theta, is going to be mg sine theta, and down here is going to be mg cos theta, right? So we resolve the force along the inclined plane, and here perpendicular to the inclined plane. So in this case, we didn't go horizontally and vertically. We went along the plane and vertical to the plane. Perpendicular to the plane. Perpendicular to the plane here, right? But what I want you to know is how do you do the, yes, Alikong?
Hey, sir, just a quick question. Some of these examples that you're giving, right? Are these some of the structure we'll be expected to see in the exams in terms of the calculations, etc., etc.?
Yes, I may give you a situation or a drawing of a situation, and I might
And then
ask
we
you
just like work
questions
it out,
based
pen
on
and
it.
paper, and then
Yeah,
okay, perfect.
yeah,
Just trying to get the idea of how we're gonna
yeah.
have to be
We're
working
gonna
this.
get some examples, and so don't worry yourself.
Thanks.
Yeah, I'm just opening up your mind to what situations you can see, right? Yeah. But what I want you to get this afternoon is this: that when you have a vector at some angle, right? Let me use the word V, the letter V, and it's making some angle, let's say theta, with the horizontal. And you have to maybe break, for some reason, you might want to break this up, right? Into a horizontal component and a vertical component. The way you do that horizontally, it's going to be V cos theta. And vertically is going to be V sin theta. Right? In the case of an inclined plane, well, you see it here. Once you know the angle that the inclined plane makes with the horizontal, parallel to the plane, it's going to be R. Well, you can see it here. Parallel to the plane is going to be R. There we say this is V. Let me erase this. Right? If you have, and you have a vector, right? Let me just put V acting down this plane. And the plane makes some angle with the horizontal, right? No, I shouldn't do that. Let's say, all right, V is acting down here. V is acting down. So the component of this vector that is acting down, the component that is going parallel to the plane is, as I said, V sin theta. And the component of this vector acting perpendicular to the plane is going to be V cos theta. Right? So I gave you both situations there. And I'll show you just now how we can have a situation where more than one vector is at work. And we maybe have to find the resultant. Right? Can I move this now?
Yes.
Good. Let's take a situation, as I said. Let me use the anybody here operates like a excavator or a drag line or something like that? Anybody in the class? Nobody? All right. Let's just see, right? In the case of a, let's say, a drag line, and there's this object, or it has to move. Now you know that, okay, the drag line might have a cable going up there. The weight of the object is coming down. And then there's another cable that might be running this way. I'm going to put it horizontally for simplicity, right? Good. So let's say it's raising 500 kg, right? Which is about half a ton, right? And the drag line is exerting an equal force to this, right? Let's go with, that will be 5,000 newtons there, right? So if it's lifting I should tell you this, right? I'm wrong in putting kg. I should the mass in the let's say the bucket is 500 kg, but the weight is going to be 500 g. The weight is going to be 500. What is g about? Weight is equals to mass multiplied by what we call acceleration due to gravity, right? And we'll use, for simplicity, g equal 10 meter per second square, right? We'll use that. So the weight is going to be 500 times g, which is 10, right? If you want to, which is equals to 5,000 newtons, right?
Excuse me, sir, I have a question.
Yeah.
So are we using the 500 grams or do we convert it to kilograms?
Oh, no, this is not grams. This is 5G is what we call
my apologies.
acceleration due to gravity, right? G is acceleration due to gravity, right? It's not grams. You get it clear? It's not grams.
Yes, sir, I
It's
understand.
acceleration due to gravity. And we'll use for most of the course a value of 10. I want to change this force that let's say this drag line is exerting to move this weight. I want to change it to maybe 6,000. I want to change it to 6,000, right? And there's a reason why. Because if the weight is this 5,000 Newton and it's lifting with 5,000, we might not get the thing off the ground, right? So we wanted to lift off the ground. And then maybe the other cable is pulling at, let's say, 1,000 Newtons, right? So let's say you have, and this is a real situation, you know, the drag line picks up 5,000 Newtons, right? In terms of whether it's sand, whatever it's lifting, right? The cable that is lifting it is 6,000 Newtons. It has a tension of that, right? And then the other cable that is pulling it, maybe it wants to bring the thing from here, somewhere here, you know, it wants to maybe put it in another location. So what's the resultant? What's the resultant force that will be acting on this mass here, causing it to accelerate and move from one place to the next, right? Let's concern ourselves with that. Now, what we see here is that we can use simple arithmetic to get, can I remove, maybe I can remove this now, right? Remove this here. So what we're trying to do now, we're trying to simplify this model, right? The model is too complex. So what we could do, we could replace these two forces. We could replace this 5,000 and this 6,000 with one force. So we have the object here. And if 6,000 is acting up and 5,000 is acting down, the resultant is a force of 1,000 Newtons acting up. You agree with that? If the weight of the object is 5,000 Newton acting down, and one of the cables on this excavator is exerting 6,000 Newtons, then the net lifting force is going to be 1,000 Newtons up. That's all?
Yes, sir.
Yes, sir.
Good. But don't forget, it also has another cable pulling it this way, right? 1,000 Newtons is acting this way. So we want to now further simplify. How is this object going to move now? Because it has 1,000 Newtons pulling up, and we have 1,000 Newtons pulling this way. We need to find what we call the resultant, right? The resultant, right? And this here, yeah. Yes, Oliver.
No, sir, just guessing. So that means that the 2,000 Newtons that are pulling simultaneously.
Oh my, somebody chopping something. Yeah, go ahead, Oliver. Go ahead, yeah.
So this question, sir, so I've been looking at it. The 2,000 Newtons that are pulling simultaneously, would those cancel out each other?
All right. You look at it. Does it look like it can cancel each other? One pulling up and one pulling towards the excavator. Maybe it's digging a trench and it's putting the mud right in front of it, the track of the excavator. Does it look like it can cancel each other? The way the forces are oriented? Watch them good.
I would say yes, sir. So the reason why I would say yeah, even I feel I might be wrong, is because you showed us earlier what Cato would be, right? For some reason, I'm looking at the um the the joining of the two arrows, which is at the dead center at the middle here, and I'm getting like zero. I'm seeing zero because they're both working together to get the mass to move.
So they're
I
not
don't
going
know.
to cancel each other. They're going to help each other. They're going to help each other. And Leonard, Oliver,
Yes, sir.
I think you misplayed days, you know. When we were little kids, right? When we were little kids, we didn't know what was a computer and internet and so, right? So you know what we used to do? We used to watch the excavator how it working, right? When you see the excavator working in my area, all the young boys gone. I'm gonna come back to the problem. And we usually would take a tinning cup, take the tinning cup, right? And we're gonna bore 2 holes on this tinning cup. And one hole, we're gonna tie a string and then you're gonna hold on to it, right? And another hole down here. And we hold on to them and throw it in the water and pull the mud out. So these two forces are going to help each other. They're not going to cancel each other. Careful with that word cancel. They're going to help each other to accomplish what you want to accomplish. So this is the bucket of the excavator. The excavator, they're down here, right? So the tracks, they're down here. The man sit down in there. And you walk in the boom, you know? So this cable, well, I put the cable up like that, right? And there's another cable working this way. So the resultant is going to be a cable pulling this way, right? The resultant force is going to be that, not the cable, sorry. The mass is going to move in this direction, right? Let me go back to the problem. So it's not going to cancel each other. They're going to help each other. They're going to help each other. Careful with that word cancel. Cancel carries the thought as though the forces will disappear. Forces are not disappearing. They're working. They're doing work. They have to be there. Right?
Yes, sir. Thank you.
Yes. Yeah, I was kidding when I say you misplayed A's, you know. But I'm going to tell you, Oliver, when we were little kids, we had to make our toys. We had to create our toys. Right? I used to take, y'all know his name, Moka Moka? Anybody know his Moka Moka? Not the place Moka Moka. The plant Moka Moka.
Sir, the thing don't scratch?
Well, if you handle it right, it doesn't scratch as much as Edoleaf. But we would make boats with Moka Moka. We'd make rafts with Moka Moka. Right? We'd make, you know, a Colgate box, but you get a Colgate box, you are a big boy, man. And we'd make trucks with Colgate box and put on wheel that is from the drinks car. You go to the shop and you ask for drinks car. I mean, make those things.
So there wasn't they don't make from them powder bottle too?
Yeah, correct. Yeah, yeah. Well, let me tell you, to get a Johnson baby powder bottle, buddy, you got to really come from a good family for get. We don't know it's powder, but it's no only people know about powder. You understand? Maybe in your time you use powder, yeah, powder bottle, that's good. When I get a powder bottle, I used to make something called puzzling cup. You all know it's puzzling cup? I don't know what that is. Puzzling cup. It's something we save coins in. We used to give it a slit and we used to nail it onto the wall. Yeah.
Yes, sir.
And-
Kind of looks like the
Yes.
regular tins, but a little bit
A
bigger.
little bit we probably call it puzzling things.
No. The Johnson baby powder, right? We would nail a nail on the wall and we would bore a hole in it and get the bottle to stick on the wall. And then we'll cut a slit on it, right? So it's on the wall. It's on the wall. So, you know, it's like this. It's on the wall, stick up there, nobody can move it. And we put a slit here, a small slit. And what we do now, every time we get like something called a bob. You ever heard of a bob? Bob was 25 cents, right? So you had 5 cents, you had 10 cents,
Dollar.
and you had 25 cents. You know a dollar yet? Dollar was a red money, a red paper money. So we will take like 5 cents, 10 cents, 25 cents, and we throw it in here, slide it in there. And we saving, like how Easter coming up. And when Easter close now, we broke it off. We broke it off the wall, and we take a knife and we cut it open, and then you get a whole set of coins. And you buy your kite, you buy your kite paper, you twine, and you make kite and you fly. And again, the kite is another good example of these forces at work, right? You wouldn't believe me. You wouldn't believe me. They have gone back. They have gone back to, they're now trying to pull these cargo ships, these ships that carry all the cargo around the world. Because of the amount of fuel needed to move goods around the world, they have gone back to using kites. It's not a widespread thing. It's still in its experimental stage, where they're using kites to pull ships along. Because remember, kites, when you put it up there, the wind takes it, man, it pulls that ship like nothing, right? They even have those that even employing sails back, right? They're all in the experimental phase because they realize that they're wasting energy. All this wind out to the sea, and you burning fuel to move the ship. No, they want to harness it again, right? Anyway, that's a little deviation from our our topic here. But let's go back to our original problem. So now, how do we calculate this resultant, right? Well, you can see here that when we complete the parallelogram, so there are two rules you can use. This is the parallelogram rule, or you can use the triangle rule, right? So R, you can see, is going to be equal to the square root of 1,000 squared plus another 1,000 squared, the square root of it. And if somebody can give me the value of that.
Sir, 1,414.21.
All right, let me go with 1,400 and what, 14? Let's go with that. Don't
Yes.
use no decimal. 1,440. 1,440 newtons. So the resultant is going to be that, and it's going to make some angle. Maybe we can find this angle now, right? So you can see that this side and this side is the same thing. So tan theta equal 1,000 over 1,000, which is 1. Theta will be equal to tan inverse of 1, which is, I think it's 45 degrees, right? So what's going to happen now is that the body, the object that this drag line is going to be moving is going to have a force of 1,440 newtons acting on it, right? And it's going to make an angle of 45 degrees. So maybe he's lifting it from here and he's taking it up there, right? Somewhere, and he's going to put it, right? What you also have to realize is that he will need to ease off these forces once the thing gets moving. But we're not going to deal with that. That's too complex. Because once the thing gets moving, as I said, and it has a certain speed, you would have to slow it down, right? And that's why sometimes you see them, they will drop the object on the ground, right? They drop the object, or they'll change the tension in the various ropes so that it goes down quietly on the ground, right? But we are dealing with a very simple situation where we started off where three forces are acting. Let's go back. The weight is acting down. There's a cable lifting the thing up, and there's a cable pulling it this way. The resultant is what we calculated here, right? The resultant is what we calculated here. How we got 1,000 acting up is that we subtracted this 5,000 going down from the 5,000 going up, and we get a resultant of 1,000 newtons pulling up. And the other cable was exerting 1,000 newtons this way. So the resultant force is what we calculated here. 1,414 newtons, acting at an angle of 45 degrees to the horizontal. And again, for those of you who are into, I mean, if you're doing this kind of work, you would have to know, is this cable that we are using here, can it deal with, remember you have a cable, 6,000 newtons acting this way, and this way you have, how much was it, 5,000? 5,000 newtons. So the tension in this thing, the tension in this cable is very large. You got to make sure that cable can take that tension before the thing cut. And when these wire ropes cut, well, you have to be careful because they tend to, be very springy, right? Remember, it's steel under tension, right? So when they cut, they lash like a whip, right? So if any of you are doing this kind of work, those are the kinds of things you got to think about, right? You got to tell your bosses, or you got to know to yourself, hey, boy, we shouldn't be lifting this amount of weight with this thing if, the rope can't take that. And so many things have to come into play, right? You have to think of that extra bit, right? What we're doing here, don't be fooled by this number. That's the resultant pulling this weight this way. But that doesn't nullify these two tensions acting on this rope. So this rope here has to withstand 6,000 plus 5,000, right? Of tensile force pulling in opposite direction. You understand? Anybody works in areas where, steel, you're dealing with what you call wire rope or steel ropes, and you see how that thing give out, how it behaves? Anybody? Nobody. Okay.
Yes, sir. Yes.
You work, okay, you work in that kind of thing. Okay. Yeah. Anybody works with GPL?
No, sir, but I work with a company that use wire rope for lifting stuff, and when the rope snap, we call it store energy. It kind of springs and hard to around the place.
Yes. If you're nearby, it's not a nice thing to be around, right? So you want to think along those lines when force, and that's what I think this part of the course should be telling you. You're being conscious of the action of forces, right? The action of forces, right? I mean, when we're talking about vectors, we're not only limiting ourselves to forces, right? We can also be talking about velocities. Like, let's take another situation. And again, we have the bridge now, but long ago we had this is the river. And when the boat, let's say, all right, New Amsterdam is here. And what is it? Rosignol? Rosignol is here. Rosignol, right, is there. Right? And sometimes you would see that when the boat leaves off here. And instead of, you would think that, man, if I'm going to Rosignol, I should point the boat this way. Isn't that what you think? If I'm going to Rosignol with this boat, I should be pointing it this way. Why do you think they don't do that?
Sir, because of the force in the water.
Yes, and then there's wind. There's wind, there's water. That person is right. And you could very well end up, because let's say the water is what we call falling. Let's say this is the Atlantic, right? The Atlantic, and the water is falling. Falling means that the tide is going down, the water is going down, the water is going in this direction towards the Atlantic, and maybe it's falling at a rate of 5 let's use km per hour, right? 5 km per hour, right? And let's say the wind, when the water is falling, the wind also might blow this direction. The wind is also going at, let's say, 8 km per hour. I'm just saying, right? And if you were to point the boat this way, and let's say the boat is going at 10 km per hour, I think I'm exaggerating these numbers. The wind might not be, yeah. So if you were to take all these, okay, if you got a boat that is 10 km per hour, right? And I wanted to give this thing a distance. Let's say, all right, I don't think it's let's say the distance between here and here is 0.5 of a km, right? 500 meters. What can very well happen, and maybe this is a problem, if you can take it down and do some analysis of it, you will see that if this thing points in this direction, let's say you make a 45 degree, right, with this bank, right? And you start off at 10 here, and then this thing is going at 5 and 8. Remember, the current is 5 km per hour, and the wind is 8 km going in that. Let's just say both of them are going there. Let's see if we can model this problem and see what happens, right? So we're going to model the problem. So you have a vector going this way, 45 degrees. And you have two vectors. One of them is, what is it? 5, this is 10 km per hour. This one is 5 km per hour. And this one here is 8 km per hour, right? So your resultant is going to be, let's call it R. So this total, this vector here, right? This vector here is 5 and 8 is how much? 13 km per hour, right? So the tide and the wind, I think I exaggerated these numbers too much. What about if I... All right, there we go, man. Yes. So your resultant is going to be what? R is going to be equal to, well, now what is going to happen here now, right? What is going to happen here now is, if you have to find R, you would have to use something called cosine rule. Anybody knows that? Anybody knows cosine rule?
Yes, sir.
But most of us don't, right? Most of us don't. So
Correct,
how we can,
sir.
yeah, most of us don't. So what we're going to do, we're going to use what we just learned. We're going to use what we just learned to find this resultant without using the cosine. It might be a little long-winded, right? But let's try it. So we have a situation where, all right, going this way is 13 km per hour, right? Horizontally. And then we have this way going 10 km per hour, right? Km per hour. And it makes what? 45 degrees. Good. So what we're going to do with this vector here, we're going to resolve it this way, and we're going to resolve it that way, right? So when we resolve it this way, horizontally, you would have 10 cos 45 degrees, and you will give me that, right, in km per hour. Equal, you give me that. And then vertically, we're going to have 10 sine 45 degrees, right? 45 degrees. Both of them should be the same. Sine and cos 45 is the same thing. Tell me what you get.
So Sir, I got 7.07 km per
All
hour.
right. Let me go with 7 km per hour, roughly, right? We're not going to use too much decimal, right? Good. So we can now take our problem, and this is what we can model it like this now. So going this way, we already had 13 km per hour. And now we have to add the horizontal, which is 7 km per hour. And vertically this way, we have 7 km now, right? So we replace this 10 km per hour with this 7 going this way and this 7 going that way. So our resultant now is going to be making use of, so we want a resultant. The resultant R, let me put 2 arrows in. R is going to be equal to the square root of, when we add these two, 13 and 7 is what, 20? 20 square plus 7 square km per hour. How much is that?
Sir, 21.19.
21 point. All right, go 21 km per hour. Don't use no decimal. Just to, I want to illustrate something. I don't care about the dead accuracy of the thing, right? So the resultant of this ship is that it's going to be traveling at 21 km per hour. And maybe we can take an angle here, right? So that angle is going to be tan of alpha will be, what's that? 7 over 20. So alpha is going to be tan inverse of 7 over 20. How much is that?
Sir, 19 degrees.
19 degrees, right? So basically, let me go back to our drawing. Let's say, all right. So our ship, if the man heads the ship, as we said, he heads the ship this way, right? He makes what, 45 degrees, we said? And he's going to go the resultant. Let's use the resultant, not the actual. He points the ship at 45 degrees, but the ship is now going to go, at 19 degrees, at a speed of 21 km per hour, right? Now, I didn't put all the numbers in, right? But let's just say, what do you think gonna happen? So this is New Amsterdam here, right? New Amsterdam Stelling. And Rosignol is here. What do you think gonna happen?
It will miss it.
It will miss Rosignol, you're gone out the Atlantic, right? I didn't give you sufficient information. I did give you this width as 0.5 km, right? What I should have given you is this distance as well. I should give you the distance from New Amsterdam to Rosignol along this bank. I needed to give you that. You know what? I think I'll send this problem. All right, let's just see. This distance was 0.5 km as well, right? So I want you to tell me between now and Friday whether the man will indeed miss the Stelling and head out to the Atlantic, or whether he will actually reach Rosignol. Right? If somebody can maybe draw it on a paper and do the calculations for us. What do you think? You can handle that? So we're assuming that, okay, the river is half of a km wide, and the river is New Amsterdam. From New Amsterdam to opposite where the Rosignol Stelling is here is 0.5 as well, right? Tell me whether this man is going to end up missing Rosignol and head out to the Atlantic rather than landing safely at Rosignol. You think you can try that? Something to think about? Like y'all don't want the challenge, man.
Sir, I guess an attempt will be.
Yes, that's what I want to hear, right? I want to see for you to let your brain go to work, right? Let your brain go to work, right? So we'll pause there, and Friday we'll continue from where we left off here, right?
Yes, sir. But sir, question. Not one not
Yeah.
question, Casey, but more like this looks like what they would tell you if you happen to fall in the river and the water's flowing stronger than you could swim. Don't swim straight across. Try to swim with the current, but kind of point yourself in the direction you want to go.
Yeah, like if you go to the beach, there's a I like that. I like that. For those of you who went to the beach, let me just mention that. So I am in the water, right? So, okay, I'm gonna draw the beach. This is the beach. Okay, this is the water here, right? And lots of times we go and we park our vehicle here, right? And we playing here, we go into the water, and I don't know, because of the current now going this way, we end up till here. And then everybody shouting, hey, y'all are going away from the vehicle we came with. We need to walk back now that way. Again, it's those vectors at work, right? Because you are in the water bobbing around, but the water and the wind is taking you this way. And that's why you end up here. And you have to go back steady. You have to go back. And that's what you're talking about there, right? You go in the, you're in the water, you fall in the water. Maybe the water is falling. Let's neglect the wind, right? If you want to head up there, you can't, well, the smart thing to do is that, okay, trying to swim this way into this current is very, very difficult. What you might want to do is while you're swimming that way and the current is pushing you, you might end up there, right? You might end up there and then rescue might come for you. Somebody might come and rescue you, right? So you can very well, yes, swim along that. But if you're smart too, you can also use the current and you swim that way. So the current is going this way. You are going that way. You might end up till here. The resultant might be something till here. And those who are coming to rescue you might very well have the sense to know that, watch, the current is going down. And if the person does some swimming, right, they wouldn't go right across. Okay, your boat, let's say your boat went down here. They're not going to go searching there unless they know. If you know the physics, you will know you can't search opposite there. Go and search this way. You understand? You think you follow it, everybody?
Yes, sir.
So you're into search and rescue. I'll tell you all about a boat incident, and maybe you can tell me yours. Yeah, you all travel Essequibo River more than me. Yeah, so you're in here, your boat goes down here, right? And search and rescue come. If the water is falling and your boat went down here, if they know the physics, they should be searching more this way, right? Or this way. It's either you swim this way or you swim that way. Even if you float with a life jacket, you're not going to end up here. You're going to end up more, at least in the direction of the current. Right? So again, if that's your profession, or you have a say in searching for people, make sure you bring in the physics, right? Bring in the physics as to where they should search. It will be useless if the current is going that way, you concentrate searching this way, right? You're wasting resources and time. People gonna die. So if you know the current is going that way, swim that. Search this way. No matter how good you are a swimmer, you can't swim against the current. As a matter of fact, I'll tell you, I am a fairly good swimmer. I'm not boasting. I cannot swim against the current in the Berbice River. It's suicide to do that. Right? If you have a life jacket, let the life jacket do the work for you. right? Just wade with that life jacket. Just try to wade and try to swim in that current. Don't swim against it. Swim with it, right? And see if you can steer yourself to the corner or wherever rescue is. Never try to swim against the current. Use the current to your advantage. All right. So I know you all have a class 7:15 and you want to probably grab a snack and so we'll stop there, right?
Okay, sir.
Yeah.
Okay, sir. Have